Howdy people, how are you? I'm going to review a solution to this problem that some of you saw yesterday as an assignment. The rest of you are just looking at a problem. So what I would do if I were you is the following. You should pause and you should read through this problem. And what I recommend you do is with some sort of, if you have this printed out, if you're just watching on video, then how do you do it? But you should try to identify the important adjectives and nouns in this description of the situation. Okay, so I'm not a huge. It's not something that I preach in terms of strategy, but there's a lot here. It's a whole paragraph. So take some time and identify things that you think are super important to your correct interpretation of the situation. Are you ready? Pause and do so. Go. Yeah, I'm still here. Are you still here? You didn't. Did you pause? You should pause. Okay, you pause. So look, here are things that I think are important. Identical blocks. Identical blocks. Okay, that means same mass. Okay, horizontal shear. Frictionless. Surface is frictionless. So frictionless. All this stuff frictionless. But all this stuff not. Color coding. Here's an important thing. I pushed with a constant horizontal force. They do the service of underlining it. Probably important. Collides and sticks to. It actually doesn't matter later on, but fine. Okay, let's sketch the speed of the center of mass, the two-block system. Now, this is qualitative in that we don't need numbers on this y-axis. All right. When we talk about, right off the rip, the speed of the center of mass. All right. Well, these two things are identical. And it means that their center of mass is always halfway between them. Fair enough? For an equal distribution of mass, the center of mass is spatially halfway between them, half the distance between them. All right. So while we say what's the speed of the center of mass, really what the speed of the center of mass is half of whatever this instantaneous speed is. And the reason that is because, look, here's the center of mass, right? Well, as number one travels from here to here, the center of mass travels from here to here in the same time. Look, A goes from here to here, center of mass goes from here to here in the same time. So VCM is always VA over 2. At least until they collide. More on that in a minute. So what we're really saying is if we can know what VA is, then we know what VCM is. They're proportional. So what does VA do? Well, VA starts, it doesn't say it explicitly, but block, no, not A, but block 1. Block 1 starts at rest, okay? Pushed with a constant horizontal force means a constant acceleration, because if net F is constant, then A is constant. And this is speed over time, so acceleration rate of change of velocity. So that's the slope of this graph. That says slope of this graph is constant. I will arbitrarily say that it gets, arbitrarily say it gets to that speed in time from time ta to tb. All right. Reaching block. So reaches point B. Block 1 loses contact and is moving to the right. Well, so now we go from here to here across a frictionless net F equals 0, A equals 0, rate of change of velocity is 0, so velocity is constant. Then we hit from C to D, and that means we have gotten to a place where velocity decreases at a constant rate because there is a constant frictional force. in that area, there's a, between C and D. So speed decreases at a constant rate. Let's say arbitrarily that it does that. All right, and then let's see. Then after D, it's frictionless again, so net F is 0. So here I'm going to say net F is constant. Here, net F is 0. Here, net F is the friction force, and maybe we'll say like negative friction force. Here, net F is 0. Now, here's where people will go screwy. Equals, there you go. They will say, all right, well, 1 hits 2, and these two things slow down, so this graph has to go to a different velocity. But look, this is speed of center of mass. All right, and if these two things hit and stick together, and you write a momentum solution, I'm not going to do it. If you write a momentum solution and say, well, what is the final velocity for when these two things collide? You get that. That's V1. That's what you get. Whatever V1 was after these two things collide and stick together, then the final velocity of the combo is going to be half of V1. Well, that's what VCM was before. VCM is always V1 over 2 because object 2 isn't moving at all. All right, and so this graph does this. It keeps on, it maintains a constant VCM. College Board loves that idea. All right, VCM does not change even when these two objects interact. And that's because there's a force on 1 by 2 that points that way. There's a force on 2 by 1 that points that way. These two forces are equal and opposite because that's the nature of forces when objects interact. And so net F on the system is 0, and that means that a system is 0, or ACM is 0, and that's the same thing as saying that the system maintains a constant center of mass velocity. Okay? So if this were a graph for object 1, it might look very much like these first sections. Yeah, sure, object 1 speeds up, object 1 maintains a constant velocity, object 1 slows down, object 1 maintains a constant velocity, object 1 then cuts its velocity in half, but this ain't a graph of object 1's velocity. It's a graph of the center of mass velocity. Okay? Now, object 1 is, at any instant, has twice the velocity of this center of mass, but that's okay. This is still can be perfectly representative of center of mass velocity. So here's the big point right here, where we separate the knowers from the thinkers, the guessers, probably, right? Constant center of mass velocity, even though objects are interacting. Okay, no change in center of mass velocity. Okay, we need to have constant slope here, right? Because we have a constant force, a constant rate of change of velocity. We need to have 0 slopes here. We need to have a constant negative slope here. All right, how far down does it go? I don't know. There's no right answer to that. But those are the criteria. Okay? All right. Excuse me. Let's see now. The plunger is returned to the. You should pause and identify important adjectives / nouns. Commence. Okay. Sphere. Okay. Constant horizontal force. Sure. Sure. Constant horizontal force. That's important. Directed toward the sphere's center of mass. Okay. Okay. Okay, so where and when does the sphere's angular momentum about its center of mass change? Well, the answer is that. All right, and here's why. If we look at any of these instances, so this is A through C and D through E. Well, no, I shouldn't say that. So B to C and D to E. The only forces acting on this object, here's a skill we should have. There's a force mg that acts at center of mass. There's a normal force here that acts at point of contact. And if we look at an axis of rotation at this object center of mass, neither of those forces can create any torque. All right, so the net torque on this object is 0, and therefore we can express torque as the rate of change of angular momentum. All right, that comes from net torque is I alpha, net torque is I delta omega over T, and there I delta omega is delta L. All right, so if net torque is 0, then the rate of change of angular momentum is 0, and angular momentum does not change. All right, however, when we take this from, hang on, when we take this to from C to D, what we get now is a friction force, hello, that looks like that applied by the surface. All right, and what that friction force does is the friction force does create a torque. All right, the net torque is now F times, if this thing has spatial radius r, it's F times r. Here's a vector, little r, to the friction force. Right, and so now the rate of change of angular momentum is F times r. This frictional force creates a torque that tends to cause acceleration in that direction, and so sure, this thing starts to roll, right? If this is frictionless in here, this thing never rolls. It never rotates at all until the friction force creates a torque that can change angular momentum. Okay? So explain your reasoning. There's why. Because the friction force exerted by the surface creates a torque that changes angular momentum. You dig? So even while this thing, now what we don't have is from A to B, okay, so we have this, we've got the mg at center of mass, we've got normal at point of contact, oh boy, we have this applied force, let's call it, from the plunger, F plunger, that acts at surface there, right? But it says directed toward the sphere's center of mass, so even FP can't create any torque, and therefore can't change angular momentum. Okay? That's it, folks. So lots of topics covered in one question, right? There's nothing that's too difficult. What there is a lot of material, right? There's dynamics, there's linear dynamics, there's graphs. Graphs are always a pain. Graphs are always challenging, I should say. There's ideas of center of mass. There's ideas of collisions. There's ideas of torque and rotational dynamics. So there's a lot of coverage in a two-part question. Okay, so very standard AP Physics 1 level stuff here. Okay.